Hi everyone, my name is Rimma, and I would be the only person in this room today who hasn't seen a single episode of Game of Thrones. Am I right? But you know what? Don't judge me, because thanks to graph database technology and my interaction with it, I had a chance to catch up. Have a look at this project. I stumbled upon it. So someone analyzed all 5 books of Game of Thrones saga and presented interactions between the main character in this weighted graph. So thanks to this graph, I can be a useful member of social club again. I can strike a conversation, say something like, hey, this pivotal node, Robert Baratheon, is quite a character, isn't he? Okay, so if we can learn that much about Game of Thrones, what sort of interactions and what sort of fights between kingdoms can we pick up in poker? Let's go. Let me first introduce VGW, myself, poker, and graph databases. Then we'll move on to data modeling with a bit of intuition on how graph database operates. And then we'll continue with data engineering, and we'll wrap up with future direction. VGW stands for Virtual Gaming Worlds. We are a Perth-based company. We were founded in 2010 by our CEO, Lawrence Escalante. He invented and patented a unique business model that allows us to enter highly restricted USA market and offer customers there disruptive social gaming experience. Chumba Casino and Global Poker are our 2 main products. And no wonder that American poker players rush to our website like bulls rush to the creek in the dry season. They were deprived of the opportunity to play poker with real money since 2010. Who in the audience plays poker? Awesome. I know what you're doing on those sites. Poker experienced massive growth. And with this growth came the growing pains, especially for data and analytics team, of which I'm part, in terms of processing, analyzing, and reporting on vast amounts of data. Ever since I joined VGW in 2017, I pretty much worked on poker exclusively, and I had to learn fast. So this is our global poker lobby. Customers can jump on the website and select the table they want to play on. So when it's dark and seems like no one is watching, some people like to do dirty stuff. So we have no idea in online poker what's happening on the other side of the screen. All these people around the table could be mates sitting in the same room and sharing information about hole cards. Of course, we have IP blocking and other ways to prevent that, but poker players are savvy, so they will overcome that. So our problem is we need to infer from the data information about their behavior and make a decision. Is it suspicious or not? But it's easy to do when you have only one table. How are you going to do it when there's more and more and more tables? All right, today I want to talk about 2 types of poker fraud. One of them is chip dumping, which hurts us, poker room. Chip dumping is deliberately losing your funds to another player so that the other player can cash out. This is called giving you ideas. And this is serious stuff. It could be money laundering, it could be terrorism funding, or it could be someone was banned from cashing out for one reason or another, and now they're trying to cash it out. Another type is collusion. This doesn't harm our room, but it harms the game integrity and other players. Collusion is cooperation to the detriment of other players. There are many types of it, but basically it involves customers or players sharing information about their hole cards and then cooperating to squeeze money out of other innocent players around the table. Current process is somewhat cumbersome. We have a fraud manager who has a wealth of experience, and he has ideas of how people might defraud our site. So he comes up with a question and asks analysts. So he might ask something like, hey, Rimma, could you please give me a report of all customers who tend to be more profitable when they play heads-up games, that's one-on-one, as opposed to when they play games with 3 or more players on the table? And I say, okay, I go away, I pre-aggregate the table, I point Tableau to it, I send it to him. He waits for it to load, then he checks it, and then he thinks, hey, Rimma, can you please give me the same report as before, but only include players who only play more than 3 hours a day, and those who never experienced play on the same table with another player of certain IP. I was like, right. So just to let you know, these types of questions is what will get you a bad name with the data and analytics team, if they're using traditional databases technology. He's asking me about relations. He's asking me about patterns. This thing has no idea about patterns or relations. Albeit the name, relationships in relational database only exist at the time of joins. And if any of the questions I voiced before sound to you like lots and lots and lots of self-joins, you're right. Alternative is graph database. In graph database, both entities and relationships are stored and processed as the first-class citizens. In graph database, everything could be either a node, something, a thing, an entity, or a relationship. In a property graph database, there's also opportunity to store metadata as key value pairs that could be hanging off any of those things, nodes or relationships. We were inspired by successes, say, when you think of graph database, of course, you think of social networks. So that's correct. Facebook, LinkedIn, Google, they all implemented their own graph database technology, which pretty much fueled their success. Here are some other examples. Novartis, a biomedical company, uses graph database for early drug discovery and genome sequencing processing. NASA stores all the knowledge they acquired over the years in graph database. And already mentioned Graph of Thrones. Okay, next section is a bit dangerous. You might start seeing graphs everywhere if you work with them for any amount of time. Data modeling. First, let me tell you a story of the person who first saw the graph. It was Leonhard Euler, mathematical genius. In 18th century, he visited the city of Königsberg, which is now Russian city Kaliningrad. Königsberg citizens like to ask a question to every tourist. River Pregel cuts the city into these 4 land masses. Now, can you walk on each of the 7 bridges exactly once and come back to the same spot where you were before? Tourists would just walk and try to prove or disprove it empirically. But Leonhard Euler was not that simple. He came up with the graph theory and the whole mathematical apparatus that comes up with it, all the theorems and mathematical notations that we use up to this day. So the answer is no, you can't, because the number of relationships coming out of the node is not even. That's so-called Euler graph. This is a simple type of graph that we saw in our data. Player plays a hand, as simple as that. Let's start here. We use Neo4j, which is the most popular graph database. We choose Community Edition because it's free, because it has a very vibrant support community. They have Slack channels, so if you have any questions, they seem to be there all the time, just answering your questions. And Stack Overflow is fantastic as well. Sorry. Okay, we also use AWS. There is Amazon Machine Image prepared for Neo4j, so it was easy just to spin up. Quite a beefy machine. I'll explain why. And we use Python because we love Python in data and analytics team. All right, so this is an example. This is a subset of our graph. In yellow, you see our players, and in blue, there are nodes. all the hands that particular player has played. We uploaded a subset of our hand data, so it's 100,000 players and over 10 million hands and about 53 million connections, which makes sense because on average there are 5 people around the table. The total store size was about 9 gigabytes, which is peanuts for Neo4j. There are examples where it processes terabytes of data. Okay, to beat the graph, you need to think like a graph. For me, coming from SQL background, I wish I had this paradigm shift a bit earlier, or someone told me that. It would save me from some frustration. But in case you may be just starting with graphs, that would be useful for you. How do we communicate with the graph database? Using Cypher. Cypher is SQL for GraphDB. It's a cool language inspired by ASCII art. So whenever you want to match a pattern, you start drawing with around brackets a node, and in a square brackets a relationship. And then you show the direction if you wish. So let's everyone for a second imagine that you are a graph database engine. I ask you, could you please, in this massive soup of people and restaurants, get me all people who liked a restaurant so that their friend also liked that restaurant? How would, this is how you would describe this pattern. Person is a friend of a person and he liked a restaurant so that this person also liked that restaurant. All right. So first of all, you have to keep this data handy. If you're gonna go to the disk every time you wanna traverse the graph, it's gonna be very slow. That's why Neo4j tries to upload all information into page cache. So that's why we need that big machine with 64 gigabytes of RAM. Next, you gotta start somewhere. So this is very important. You have to start with the nodes, right? So to save Neo4j from initializing every single node in this graph database, this is where labels came into play. If you properly design your graph database and you labeled nodes accordingly, you're only going to start with people and leave outside all the nodes you're not interested in. And indices. Neo4j supports indices on node properties, so if you're interested in a particular person, then you don't have to go through all the nodes and find that one. Indexes will help you. And then you start traversing out of those nodes. Traversing is where Neo4j shines. Because of the architecture of this database, every relationship is stored as doubly linked list. So moving from one node to another is a super efficient operation. What can help there, though, is a relationship type. Just type your relationship appropriately, friends of, likes, restaurant, etc. So we don't have to go out into every single relationship. Okay, quick recap. This is a so-so query. Doesn't give graph database much information. This is better. We labeled it. Now we know where to start. This is even better because we're starting with Jack and we have index on Jack, on name property. This is even better again because now we have typed relationships and RAM large enough to store the graph. Also, please set this setting. And Java heap space large enough to store intermediate results. Okay, let's have a look. Demo time. So I start the engine, and just like in a winter morning in Russia, you have to first warm up your engine. So this procedure tries to touch every single node in the graph and put it into page cache. So the queries would be faster. Okay, so say I'm interested in chip dumping scenario. I want to see all players who came to our site, got their $2 sign-up bonus, and then lost it straight away to someone. In itself, it's not suspicious, but this is a start. Oh, here they are. So you can see on the relationship They lost $2 to someone else. Okay, let's expand this graph and see who did they lose those $2 to. Cool. You see, now we see that it lost $2 to someone else. Again, in itself, it's not very suspicious, but if we see this behavior repeating over and over again, if someone seems to make money off innocent one-time butterflies, that's not a good thing. For example, like this guy. Check him out. All his, sorry, you probably cannot see, but he collected lots of bonuses from other players. Okay. Let's leave only suspiciously lucky people, only those who made all their profits in our game by winning bonuses from other people. So just a quick look of this query. First, I match everyone who plays a hand. Then I also only leave out those who played only one hand and lost the $2 thing. Then I pipe this data into the next part of the query. I'm looking for those who won that money, and then I group across them based on their winnings. Let's run it and see what it returns. This time, I instructed the graph database to return a table. This is interesting. Have a look at this guy. All his wins in total lifetime was $438, and exactly $438 came from bonuses. So that's not good. We can stop here and start investigating one by one. Did he try to cash out, or what was behavior after that? We can also do some cool stuff, because Neo4j comes with a full-blown library of graph algorithm. So, for example, famous problem, degrees of separation. As you know, everyone in the world is separated by 6.6 hops. Let's see what is it like in our poker room. This query is going to run about 9 seconds. And the answer is 4. You can see that the maximum length of all shortest path is is 4. So that's interesting. Everyone's separated by 4 nodes in our database, 4 hops. Right. Another graph algorithm that is quite interesting is Dijkstra. So this algorithm works every time you open your Google map and try to navigate from point A to point B. It uses weights of the relationships to come up with the shortest path. So for example, we can look at that guy who won $430 and see where did the money travel from then on. We can see, investigate this whole pattern with other players. Okay, that was a short demo. Let's go back to the presentation. Okay, so how is it even going to work, all that? This part wouldn't be possible without Denis Lapchev. He helped a lot. He is a Grand Python Meister in our team. We ingested data into Neo4j just as a one-off for this proof of concept. And it took minutes from production Redshift to S3, then from that S3 to destination EC2 minutes, and then actually ingesting data into graph database, all these millions of nodes took about an hour. And I think that's a plausible solution, because it's not going to happen more often than once in a quarter. So how is it working now? Right here down at the very end, you see our fraud integrity manager with a big band hammer. So we exposed Neo4j browser for him, because it's a great tool to visualize. So he can ask his question directly through Neo4j browser. He's learning Cypher, and it's easy to learn. So even your business, I shouldn't say even, your business users can use it, no problem. And we also have Slack bot, again, written by Denis. And this bot listens to the channel, and it can interpret queries. So we instructed it to understand Neo4j queries, and we have 2 paths. One path is for short queries, for synchronous queries. and another path for longer running queries, asynchronous path. That's because Neo4j does not support asynchronous queries. If once you ask it a question, you can't leave it until you get the answer. So hence, Flask, a web server, takes care of that. It spins up a new process every time we ask a long-running query, and then it pushes the result into S3. Lambda picks up the put event and sends it back to Slack. So yeah, this is a screenshot of Aniken, the bot, answering the question. What's next? Future direction. We take great consideration in personally identifiable information and security. So our next step is to work together with TSS team. They don't know about it yet. But now next step is to ask them to secure the Neo4j database properly, put it into the same sort of environment that our other databases sit in, so that we can populate it with more interesting data. So we can add addresses, names, emails, cash outs, purchases, tournaments, IPs, and then we can really, really have fun trying to find those fraudsters. That's it. Do you have any questions?